We can get started while folks are joining in. Good morning, everyone, for today's distinguished webinar series in AI and cybersecurity. Today's distinguished speaker is Georgios Fragkos, Principal Member, Technical Staff, Sandia National Lab. The title for today's talk is How Can AI Help with Cyber-Physical Security in the Electric Grid? Dr. Georgios Fragkos is a principal member of the technical staff at Sandia National Lab. His current research focuses on AI and machine learning for CPS, including cybersecurity use cases such as threat detection. He obtained his 5-year joint diploma degree in computer science from the National Technical University of Athens, Greece in 2018. He received his MS and Ph.D. with distinction in the field of computer engineering at the University of New Mexico. Dr. Fragkos was awarded the UNM Graduate Excellence Fellowship in 2019, the School of Engineering UNM Outstanding Graduate Award in 2020, and the IEEE Outstanding Graduate Engineering Student Award in 2020. Dr. Fragkos, and thank you so much for joining this webinar. I appreciate for you, it's a great honor to have you on as part of the webinar series, and the floor is yours. You can start your presentation.
Perfect. Thank you so much for inviting me, and I'm happy to share with you this talk. So let me share my screen real quick. Can you all see my screen?
Yeah, but it's not at full screen. Can you make it full screen?
I can do that. Let's see. Can you see it?
Yes, that sounds good. Thank you.
Perfect. Okay. So thank you for inviting me. My name is Georgios Fragkos, as you mentioned, and I'm a principal member of technical staff at Sandia National Laboratories. I'm an engineer at the Renewable and Distributed Systems Integration. And today we're going to talk, And today we're going to talk about how can artificial intelligence help with cyber-physical security in the electric grid. So first of all, I'm going to talk I'm going to give some introductory notes about the cyber security within the power grid and why do we need cyber physical analysis. And then I'm going to also provide some information regarding artificial intelligence and machine learning for cyber physical security in the grid and why do we need that. And after that, I'm going to provide you with 2 use cases that we have researched at Sandia National Laboratories, and we have published the papers on these 2 topics. First of all, we're going to see how offline deep reinforcement learning can be used for developing dynamic access controls that actually protect the grid and ensure its resilience. And then we're going to move from the access controls towards how can we use autoencoders in order to perform data fusion, and how can data fusion help us with threat detection. So the modernized power grid has undergone a very big transformation in the recent years, right? So first of all, we have high penetration of distributed energy resources. We have wind, we have electric vehicles, we have large solar panels farms. So this means that these DERs are integrated with cyber communication networks, right? So we have a combination of cyber components with modern physical components, right? So this results in vast amounts of cyber and physical data that are generated by the different DERs. And these DERs can talk to each other with a lot of different protocols. We have Sunspec Modbus, we have IEEE 23.5, which is a really new protocol. We have DNP3, right? And then we have interoperability standards like IEEE 1547. So we have all of these communication types, we have all these interfaces within the grid, and the DRs are trying to talk to each other. So we have to find a way to, first of all, ingest and process this cyber physical data. And then we have to implement and design different mechanisms in order to protect the grid's integrity, and also protect threats that can disrupt its functionality, right? So we have some examples of cyber attacks. For example, we have the 2015 Ukraine grid cyber attack, where about 300,000 customers experienced outages, hundreds of servers and workstations were damaged, and megawatts of power was lost, right? So the question that we're trying to answer at Sandia National Laboratories in my group is, how can we use high fidelity cyber physical data in order to protect the cyber physical power grid? So first of all, I want to mention how artificial intelligence can be used for cyber physical security in the grid. First of all, artificial intelligence can provide us with autonomy and intelligence. What is the ultimate goal, though? The ultimate goal here is to create decision-making mechanisms that can actually operate on behalf of humans, grid, and operators. And we want these AI models not only optimize the immediate state of the system, but to have a long-term impact on the system, meaning that long-term, it will protect the grid. However, there are some application-specific challenges when we are building AI models for cybersecurity. First of all, in cybersecurity, we have a difficulty in achieving a satisfactory decision-making workflow. So in cybersecurity, if you think about it, what is considered satisfactory, right, for an AI model? Most of the times we talk about accuracy. So if we have like a 90 or 95% accuracy, we consider it really good. But cybersecurity is not a recommendation system. It's not a ranking system. So this means that even if we have 95% accuracy, because the data sets are imbalanced, the bad data are much fewer than the good data. This means that a high accuracy doesn't mean that we have minimized the false positives and false negatives. So this is a difficult thing to overcome. Additionally, we want these systems to operate on behalf of humans, which means that we also have to instill some trust on these humans, right? And then, as I mentioned, the use cases that we're exploring are critical. So they serve the US critical infrastructure. So we have to make sure that we ensure the uninterrupted operation of the power grid. So the first case that I want to show to you is how can we use artificial intelligence, specifically reinforcement learning, for dynamic access controls in the grid, right? So what we really want to do is introduce some decision-making computing systems that can actually create some access controls within the DER ecosystem in order to protect the grid from malicious users and maybe from insider threats. A note here is that when I say decision-making, I mean we need an AI model that learns the best action to take given a set of discrete actions. In these AI models, we also want to inject human cognizance in order to make sure that this AI model doesn't just look at the cyber part, but also, for example, at the behavioral of the users within the system. And then, because if you think about the user can be malicious or bad during, a big time period, we have to make sure that we can focus on the potential sequentiality of this problem's nature. So here, I want to try to give you an overview of what I mean by sequentiality and non-sequentiality, right? So for decision-making, we may have some non-sequential models, machine learning models. So the non-sequential machine learning models, they just have some features, right? Some characteristics in the system, and they only care about taking the best action possible in order to maximize the immediate reward. So to just take the best action right now, kind of a greedy approach, right? Now, these models, since they want to maximize the immediate reward, they can be characterized as short-sighted. However, the sequential models are kind of different. The sequential models try to look into, a lot of states, like in a long time period, right? And they may, like in a specific state, they might take a suboptimal action, which provides a lower reward, but this may lead the system to a higher long-term reward, because the focus of the sequential models is to maximize the long-term reward. Now, the sequential models, they are considered to be far-sighted because they're actually trying to maximize this long-term reward. Now, having this in mind, we are all familiar with non-sequential models, right? Like 99% of the supervised learning models, are like SVMs, random forest. They are all non-sequential, and they're trying to maximize the long-term reward. And we also have contextual budgets, right? Like they're used from Microsoft, for example, for recommendations and for rankings. Now, the sequential, the most, in my opinion, representative machine learning paradigm for sequential modeling is reinforcement learning. So reinforcement learning is a sequential decision-making paradigm that learns how to perform decision-making based on the immediate and future impact or reward of the actions. And they are trying to maximize the long-term reward. So now all sequential decision-making problems can be formulated as an online reinforcement learning decision maker. So this reinforcement learning decision maker interacts all the time online with an environment, with a stochastic environment, and learns by trial and error. So as the time goes by, the agent becomes better. And based on that interaction and the observed experiences that the agent collects, this reinforcement learning agent learns to optimally determine the best actions and decisions to maximize a long-term reward. Now, as I show here, the online agent can be a data structure, like a table, for example, if you have very few characteristics in the system, but it can also be a nonlinear function approximator, a deep learning model, for example, right? And it just tries to maximize the long-term reward by taking some good actions. But there is a but here, right? At Sandia, for example, and the utility companies, we have prior log data. We have huge data sets that we could use it in order to train some models, right? So, with online reinforcement learning, we cannot really use this data. Additionally, the online reinforcement learning paradigm, as I mentioned before, assumes that the decision maker interacts with the environment and learns the optimal policy using its own collected experience. So it interacts online. However, if you think about it, we have a cybersecurity use case, right? So we cannot really say to a utility, hey, we build this online reinforcement learning like model. Can you please deploy it online and see if you can perform threat detection? It's not realistic, it's unsafe, and it may cause millions of dollars loss, right? So what is the solution here? The solution is the offline reinforcement learning. So the offline reinforcement learning, sometimes in the literature, you can also hear it as batch reinforcement learning. So this thing is inspired from the success of supervised learning. And in my opinion, it's a data-driven reinforcement learning paradigm. So what happens is that it utilizes only previously collected offline data. For example, it can utilize the data that we have collected, from the utility companies or from some of the national labs, and we don't need any additional interaction from training, right? So this means that we can train the reinforcement learning offline by creating some Markov decision processes, and then only when the reinforcement learning agent is fully trained, then we put this agent out there in the production, and it performs the same way that a trained online agent performs. But we are sure that it's safe. So how can we use this thing in the grid, right? So our idea is, can we utilize offline deep reinforcement learning in order to create dynamic role-based access controls for smart grid applications? So this was published in the IEEE Transactions on Human Machine Systems. And what we did is that, first of all, role-based access controls, I'm sure that you're all familiar with RBAC. It's a role-based, policy. So this means that you have some subjects, some users in your system. For example, some employees at a utility company, and these employees have different roles. They may be utility engineers. You can also have DR owners. You can also have DR vendors, right? Like Tesla. Now, each of these roles gives specific permissions to objects. So if you have DERs, and if you're a DR owner, you can read your DER settings, right? Now, if you're a DER vendor, you can read or write the DER settings. So the permissions are assigned to the subjects, to the users through the roles. That's the essence of the RBAC. Now, in this model, and this model is used a lot by utilities. Now, we identified some problems in this approach, right? First of all, the DER ecosystem has so many users, roles, and permissions in DER organizations. And it's really difficult to efficiently manage the RBAC roles, right? Because they have security engineers that actually manage this RBAC system. But most of the time, because it's so complex, it remains static. And another problem is that you may have users within your ecosystem that their behavior may change. And when I say, behavior, I mean, think about insider threats. You may have an engineer that, he's a really good engineer. For 2 years, he's working perfect, but then he's trying to act maliciously within the DR ecosystem, and he tries to sniff, for example, some traffic. So how can we make sure that we represent how often a user may act maliciously, and how can we make sure that we protect the system from these behaviors? So the key ideas here that we had is, first, we should build the behavioral profiles of the DR users as features, as characteristics in the system, and then actually use these characteristics to build a dynamic RBAC policy based on offline deep reinforcement learning. So this is our main, I guess, idea here. I don't want to go deep to, to the math part of it. I just want to give the overall idea, and, of course, feel free to check our paper online. First of all, we already had an intrusion detection system that was particular to specifying if there is an insider threat going on, right? So this intrusion detection system at Sandia was able to check if the action of the user within the DR ecosystem was good or malicious. So by deploying this tool within a test DR ecosystem that we built, we were actually able to create the behavioral profiles of all the users, DR owners, DR vendors, security engineers of a utility, right, throughout the time horizon by utilizing a math equation. It's kind of simple if you see the equation, by utilizing which is called the Bayesian belief distribution. So this distribution is simple. You can think about that if a user acts good, then the trust for the user in the system increases. On the other hand, if this user starts acting weird based on the intrusion detection system output, this trust goes down, decreases. So we were able to model the whole problem as a sequential decision-making problem via a Markov decision process. So here I'm showing the states, the actions, and the rewards. The states is what is the user ID, what is the requested role for a specific action, and what is the trust of that user within the system, right? So then the model should can perform one of these two actions, either grant authorization to the user to perform a read-write based on the requested role, or withhold authorization. And the rewards is either one for the case that the user is authorized and he does the action and the action is good, so we have a good behavior, or it's -1 when the user is authorized, but the intrusion detection system saw that, oh, this action may be malicious, but the model actually gave the authorization. And then we have a neutral reward, which is 0.8, when the user asks for a role, but it's already not authorized for this role based on the base RBAC system that we have. So what we did is that we actually utilized offline reinforcement learning to train offline the agent on this user activity that I mentioned, right? We have trust, we have some requests, we have user IDs and role IDs. And what we tried to do during this offline training is that the model should be able to find if there are any behavioral deltas for the users. So this means that a user may be good, at some point it becomes bad. So at this point, the model has to withhold authorization, right? So if the model finds a behavioral delta while it's like deployed in the production, this means that it should withhold authorization for that user, for that specific requested role that previously this user had the role, right? And it updates the RBAC model that we have. So at the bottom there, you can see mainly the idea, like, you know, the flow, the request flow within the system, and also the block diagram. So I want to mention, I explained how the, you know, this whole system works, but the block diagram, you can see that we have a base RBAC policy on the right, I mean, right? And then we gather a lot of requests from users and roles ID, right? We deploy this intrusion detection system. The intrusion detection system says that's good or bad. We update the Bayesian belief, and all of this like stack of information, we save it into a replay buffer. And then the DQN, the reinforcement learning agent, actually is being trained offline. And only when this is fully trained, we deploy it online, right? And then it takes decisions based on granting authorization or withholding authorization, and the RBAC model is updated. So here, these are not all the results. I just wanted to show you, you know, the main points. First of all, I'm just showing the temporal difference loss for the training of the offline reinforcement learning agent. So you can see that, you know, the temporal difference loss goes down. So this means that we have convergence, right? And then you can see the action distribution, right? So again, action B is withholding authorization. So the model saw a behavioral delta of the user, and it's like, oh, I have to, you know, protect the system, so I'm taking back this role from this user. And action A is granting authorization. So you can see that the DQN, the offline deep reinforcement learning, increased the times that it said no to a user. And this is because it actually observed some bad behavior from a user based on the Bayesian belief distribution. And it also decreased the number of times that it says yes. So at the bottom diagram, I saw the security accuracy increase. When I say security accuracy, I mean, how was the model able to mean, how much did the model decrease the number of false positives and false negatives within the system? And we saw that our approach, which is called as hybrid, because we have the RBAC model and the offline deep reinforcement learning that actually changes this RBAC model based on the behavior of the user, actually had the biggest increase, right? So we had like a big minimization of false positives and false negatives within the system regarding, you know, access requests. And we compared this with a lot of machine learning models, mostly sequential models, right? Plus some static models like RBAC1, which like is static. It's the classic RBAC model that the utilities use right now. So this was the first use case. Now, the second use case, we want to move a little bit from sequentiality and go to non-sequentiality. So a big part of the research work that is out there tries to utilize deep neural networks for identifying only physical disturbances in the grid's measurements. And they are doing it very well. Like another big portion now, they are also trying to perform threat detection by only checking the cyber data that originates from the IT environment of the grid, right? So we identify the gap regarding how can we blend the physical with the cyber data. And this effort is also funded by the LDRD office at Sandia. So the question that we're trying to answer here is how can we effectively fuse the cyber with the physical data that is generated in the grid? And how can we do that in order to ensure situational awareness and detect not only cyber threats, but also physical disturbance at the same time? So what do we propose here? We propose a cyber physical threat detection methodology using data fusion. What do I mean by data fusion? I will talk about in a little bit, but in order to do that, we explored the solution of a long short-term memory autoencoder. Why did we do that? Why did we combine LSTM with autoencoder? Because except the structural patterns, we also want to capture the temporal patterns of the cyber-physical data, because the data that is generated in the grid is time series, so we don't want to lose this specific information. And we generated this data by using a Sandia's testbed that simulates realistically a part of the electric grid. Also, this effort was published in the, I think I have the title wrong here, but it was published in the IEEE Kansas Power and Energy Conference 2024. So again, you can reach out to me and I can give you more information about it. So for the electric grid testbed and dataset, I'm not gonna go into deep detail, but at Sandia, we have a testbed that uses a real-time digital simulator and Septre, which actually gives us the opportunity to design and implement and model a comprehensive ICS SCADA model, right? And we can actually perform, for example, we can actually explore different events, different attacks, different bus systems, right? So with this testbed, we were able to collect cyber features that were collected from three different relays in each of the three substations, right? And we also had a lot of physical features, for example, frequency, per phase voltage, per phase current. And the overall system that we modeled is a simple one, the WSEC 9-bus system, in order to showcase what we're trying to prove here. What is the threat model? First of all, we have physical events, right? Where we have a generator and line outage event, and the mitigation for that would be to perform a load setting. We have a cyber event, for example, a denial of service attack, and we have a cyber physical event where we actually combine the cyber and the physical events, right? So this is our main use case. So we have the generator and the line outage events happening at the same time. And at the same time, we also have a denial of service attack that actually impedes the load setting signal issued by the control center. So we can consider our use case as a cyber physical event with no mitigation. So we don't have mitigation in the system. So this results in an unstable system as defined by frequency instability. Now, we want, like after we collect this data and we have all this, cyber physical combination, how can we analyze and extract meaningful insights from this fusion, right? Why do we need to combine and analyze together? First of all, at machine learning, we've seen that when the dimensionality of the input space increases, so we have a lot of features, like hundreds of features, the complexity of the classification task also increases. And this means that the accuracy of the actual trained machine learning model increases, right? So we want to figure out how we can reduce the dimensionality of the input space in order to enhance the predictive performance of classification models. And how can we actually do that in order to perform effective threat detection? So there are, for example, two approaches that you're really familiar with. I'm sure about it. We have the PCA, principal component analysis, and the LDA, linear discriminant analysis. But both of these approaches mainly assume that the data lies on a linear subspace, which is not always true in real-world scenarios, especially in a cybersecurity use case, right? So that's why we actually moved away from this kind of approaches. Now, what is the data fusion, right? What is like the combination of cyber and physical data? So we have a high-dimensional cyber-physical input feature space, and we are trying to create a manifold or a code, you may see it as a code in the bibliography, that actually represents, the most valuable information that we originally had, right? So what we want to do is perform the data fusion, and by preserving the relationships between the cyber-physical data points through manifold learning, we want to have a lower dimensional space, right? And perform threat detection and have very high accuracy because, again, it's cyber-physical threat detection. How are we able to do that? in order to do that, we use autoencoders, right? So first of all, for those of you that you're not familiar with the autoencoders, they're a type of symmetrical artificial neural networks, unsupervised learning, right? ANNs, and they are used for compression of the data. So in our case, for dimensionality reduction, right? And if we specify it more, for data fusion. Why? Because if you see, we have like some cyber physical readings that go in the autoencoder, right? In the first part, which is also named an encoder, this data gets compressed until they reach to the final like version of the compressed data, which is the manifold or the code. And then the autoencoder actually decompresses the data. And what it does is that it outputs reconstructed cyber physical readings. And then the question is how it's trained, right? It's trained based on the initial cyber physical readings and what it reconstructed, what it output, right? So the autoencoder compares these two like feature values and it gets the reconstruction error. So the difference between the initial features and the reconstructed features. And as I mentioned before, instead of just building the autoencoder with the classic like ANN units, we used RNN units, and specifically recurrent neural network, and specifically LSTM units. Why? Because the LSTM units can actually capture the temporal patterns in time series data. So the LSTM architecture within the autoencoder helps with memorizing what happened in the time series, right, of like cyber physical data, of a cyber physical event, and it informs the model about potential future cyber physical patterns. So here, again, I provided some results. First of all, in the left diagram, I present the normalized average like value of all the features, right? So you can see that the normal data has a clearly different pattern from the abnormal data. And the abnormal data also has a lot of noise. So this means that probably, a good trained model should be able to find this difference. So what we did is that we created a model, right, an LSTM autoencoder model, and we we trained this model only on good data. So most of the times on the grid and cybersecurity use case, we don't know what is a bad data. Every day there are new cyber attacks, there are new sophisticated attacks, right? So we wanted to be realistic, and by being realistic, we just simulated only good training data. So we trained the autoencoder with this data, and we performed a hyperparameters optimization with grid search. So we optimized the number of layers, the weight decay value, the learning rate, dropout rate, batch size, optimizer, and how much we reduced the initial feature space to the code, right? So with green color, you can see the chosen hyperparameters of our LSTM autoencoder. And on the bottom diagram, you can see that we were able to minimize the training loss and the validation loss, which is an indicator of convergence of the training of the model. And again, I want to point out that we trained the autoencoder model only on normal data. Now, why did I mention that a couple of times? Because by training the autoencoder only on normal data, will provide us with a threshold for threat detection. So what does that mean? This means that if you see on the top left screen diagram, you can see that we measured the reconstruction error distribution for the normal data, for new unseen normal data of the trained LSTM autoencoder. And you can see that the range for the reconstruction error for the trained model is, let's say, between 5 and 9, right? So what we understand is that when the autoencoder sees a normal data, the reconstruction error should go somewhere there, right? Like between 5 and 9. But if the autoencoder sees something weird, that it's not trained on, the reconstruction error should identify it as abnormal. How? Probably this reconstruction error should be much higher than 9. So our threshold for threat detection through the data fusion that we performed is 9. So this means that if we see a data point that has a reconstruction error higher than 9, is abnormal to us. And then we fed the autoencoder with abnormal data points. And you see on the middle diagram that the reconstruction error of the autoencoder for this abnormal data is between like 30 and 50. So it's well beyond our threshold. So this means that the autoencoder, based on this threshold, is able to figure out that, hey, something's going wrong, right? And then in the right diagram, I presented on the top row 2 normal data points, the initial normalized values, which is the blue line, and the orange line represents what the autoencoder was able to reconstruct. And you can see that in the top row, which is, again, normal data points, the autoencoder was able to reconstruct it perfectly. The 2 lines are almost matching, so that's why the reconstruction error is very low. Whereas on the bottom row, you can see that the orange line, so what the autoencoder reconstructed, is not really aligned with the blue line, which means that it's not really able to reconstruct the abnormal data, right? So that's why we're able to perform threat detection. And on the table, we tried to answer the question, and how did like cyber physical fusion help with that, right? So we measured how did cyber physical fusion help with accuracy. What if we used only cyber data? And what if we used only physical data for threat detection? So you can see that in all 3 cases, we had high accuracy, but only for the cyber physical data fusion, we had 100% accuracy. So 0 false positives and 0 false negatives. Now, again, going back to the start of my presentation, I want to say that here you may see like 96% and 98%. It's really important to think that it's not recommendation systems and not ranking systems, right? It's a cybersecurity use case. So this means that a 96% from going to 96 to 98 is really important. And from going to 98 to 100 is extremely important, because what matters in cybersecurity is the number of false positives and number of false negatives, right? So this is all from my side. Thank you so much for being here and seeing my presentation. Please contact me if you have any questions. FYI, we're also hiring for some postdoc positions, so please reach out, and I would be happy to talk with all of you.
Thank you, Dr. George, for your presentation. We'll try to grab some questions, and maybe I'll start with the first question. Could you talk about, how you compute the data density for normal and abnormal computation that you had in your slide? Could you spend some time on discussing how do you do that?
You mean these diagrams here?
Yes, with the reconstruction errors and y-axis.
Right. So what we did is that after we trained the machine learning model, is that we had some new unseen normal data, right? So we had the trained model, and we just fed the normalized normal data to the autoencoder, right? So the autoencoder was able to compress this data, and then through the decoder part of the autoencoder was able to decompress. So what happened is that we just measured the error between what we had initially fed to the model and what the model actually output, right? So here we actually present the histogram, so bins of, I think, 90 data points, and I don't really remember the exact number, but we present the histogram of this reconstruction error. That's what I'm mentioning here. And the same holds true for the abnormal. So we present the histogram of the reconstruction errors of abnormal data points by just feeding abnormal data points to the model, just in order to see where the reconstruction error, falls. Does this answer your question?
Yes. So you got that threshold of 9 from this normal. Why does this keep on going?
Yeah, I don't know. I'm sorry for that. It's just weird.
Okay. Okay, interesting. But in terms of the next slide on next chart on the abnormal density, so the y-axis is a little different than x-axis, but also the 30, 40, 50, these are epochs, or what are these?
The 30, 40,
Reconstruction.
50 are like the reconstruction error, the value of the reconstruction error of the bins of the data points that we gave to the model. So bins of 90, data points have reconstruction error between 30 and 50, So that's what you see on the x-axis. It's the reconstruction error value.
Could you talk about the type of signatures you had for cyber as well as for physical? You showed one thing for a normal and abnormal signature. That's just a simple signature in time series. But I'm just curious to see what exactly you mean by physical signatures. And by looking at the training time and the testing time, for some reason, you have both physical and cyber physical requires, 0.8 seconds, So why do you think it takes the same number of time in a runtime, for physical and cyber physical?
Yeah, that's a great question. So first of all, let me just go back. Where is it? So for example, for the cyber events for that paper, we had a DOS attack, right? So it was like a simple attack with some physical events that the utilities have mentioned that this happens, right? And we just, we published only this attack just because to showcase that this may happen. Now, the physical features in the dataset were about 100, and the cyber features were about like 10 or 12. So we had, retransmission times, we had, round trip times, packet retransmissions, MAC addresses, IP addresses, and stuff like that. So that's why the testing time between the cyber physical and the physical is almost the same, because the majority of the features are the physical features, right? We also performed some experiments where we put more cyber events. And for this attack, it didn't really help, it didn't really make a huge difference. Now, we are considering, actually, we're currently doing some other attacks that, I cannot really say right now, but we are taking also other attacks that are more stealthy, So for example, the DOS attack, you can see just a high round trip time. So the high round trip time actually gives us the information that we want. But if you have, for example, a man in the middle that tries to mess with the JSON messages within the packets, that's much, much stealthier. So you have to have cyber features, cyber signatures that actually gives us information about the JSON structure of the packet, if this makes sense.
Thank you. I'm reading the questions. What are your comments on running these models on edge devices? Are the encoders built with this that they would run on remote servers or locally on edge devices?
That's a great question too. So right now, the last stage of the project is to actually deploy these models within, like, in Raspberry Pis, like that kind of simulate an edge DR device. And we are currently building an API to do that. So we have a timing constraint, which is like the whole API functionality. So getting the data from a database, just like doing the detection should be under 1 second, all of it, right? Right now, we've seen that we're okay with that constraint. Now, again, we have to explore if we have stealthier attacks, so this means more features, how this is going to work. Right now, yes, it does work, and we are successful in deploying it into edge devices. The train model. The training should happen offline, of course.
Okay. Let's see. Okay. What about have you thought about transformer attention mechanisms, graphs to advanced detections? Do you think it's necessary to expand the LSTM setup?
Sorry, can you say again the question?
What do you think about next steps after LSTM? Do you think it's good to include extensive and attention mechanisms and transformer networks, graphs to advanced threat detection?
Yes.
Actually, do you
Yes, I think combining the autoencoders with like graph neural networks just to provide situational awareness within the grid, it's one thing that we're currently exploring, and we're thinking how to do it. But again, like our main concern is the timing, because this thing has to be realistic and has to run, as you mentioned, in dense devices. So we are trying to keep the pipeline simple. So if we can detect a threat without using a model, that's great. So only if we need to use the machine learning, we are using it, right? So, for example, the graph neural networks have high complexity, right? But they provide great situational awareness. So we're exploring it, but we're not sure yet about the final outcome. But it's something in our to-do list. Yeah.
Thank you. What insights are hidden Markov models giving you over other options?
So, for the first of all, I want to mention that the Markov decision process somewhere. So the Markov decision process provides us with chains, let's say, of events that help us understand what is the user behavior throughout the time period. So that's a good question again, because I want to mention that in this specific use case, we have a Markov decision process for every user. So this means that we don't have a Markov decision process, a universal Markov decision process that describes the problem. And if you see in the state, I have this user ID. So this user ID actually is the ID that also provides, the ID for each user's Markov decision process. And the main insights that the MDP gives us is, first, it allows the reinforcement learning to work, right, and converge, because most of the times when you're trying to use reinforcement learning without an MDP, it doesn't really converge. And if it converges and you put it out in the production, you're going to have distribution problems, like probably in a couple of hours as soon as the distribution starts changes. So it provides us with stable convergence, and it also provides us with the ability to actually identify if there is any behavioral delta at a user's MDP.
But what specific thresholding techniques did you use? Did you use any static or dynamic thresholding techniques to classify normal, abnormal, or can you talk about specifically how you compute the reconstruction loss?
Yeah, so the reconstruction loss was computed really, really simply, I guess. So in order to compute the reconstruction error, we just used the MSE, the mean squared error of what we gave as readings to the model and what the model reconstructed. So by just getting, for example, not the MSE, sorry, it's the L1 loss. By getting the L1 loss, and training the model with this L1 loss, we were able to put the threshold. And the analysis that we did is static. This means that the threshold remains the same while the model is in our production. But when we see different distribution, like in new upcoming data, so for example, if we see that an indicator that the model underperforms, like the false positives or false negatives, go up, this means that we take offline the model, we perform recurrent training, so on new data, and then we compute a reconstruction error. And because the model is trained using a warm start, it's already trained, it just may see like some new data. The training time is very, very low when we perform, a training like after it's being deployed.
Super. We have a question from Dr. Jun Liu. Whether the hidden Markov chain trained from learning only serves to provide a classification of raw data.
Sorry, I'm not seeing that. What was that? The hidden Markov? Can you say again the question?
Let me make Dr. Jun Liu on the panel so he can ask the question.
Yeah, great.
Dr. Jun.
Oh, okay, thank you. And so since you just mentioned about the hidden Markov chain that's trained from the raw data, so since I have used a hidden Markov chain beforehand, it seems to me that the hidden Markov chain mostly serve for providing the, some initial classification or clustering of the data. And that, however, as for how to interpret it, because in the hidden markup chain, in the end, it will produce the number of states. So it is really up to, the user to try to interpret the meanings, associated with each state. Am I right in your case?
Yeah, so that's correct. The thing that helped us with interpreting this result is the trust that we used for the Bayesian belief distribution, right? So when the model, was taking an action, for example, classifying, as you mentioned, like I'm withholding authorization, we were also checking if there was any delta within, the last like 2 or 3 time steps in this specific behavioral profile. And if there was a significant decrease, then we were actually interpreting the state by saying, oh, okay, so the reinforcement learning model said no. We also see, a big value in terms of decrease in the behavioral delta. So we have to withhold authorization. And also, what we did is that based on how much decrease we were seeing, the number of false positives and false negatives was actually changing, as you mentioned, right? It's open to interpretation. So what we understood when we were talking with utilities is that the utilities are able to make it as strict as they want based on their interpretability.
Does that help, Dr. Jim? Okay.
Oh, yeah, thank you. Thank you. Yeah, very, very good. Okay, thank you.
Of course.
So we have a lot of students listening to your talk. What do you think people are listening to you to as a takeaway message to look at deep reinforcement learning, or especially on the DER context for cybersecurity? Can you talk about some interesting that or research directions?
Sure. From my side, I think something that really interests me right now is, first of all, how cyber physical analysis can help with cybersecurity. Most of the times, like in the past years, we're focusing a lot in cyber events. As I mentioned at the start of my talk, the grid is modernized now. We have a combination of cyber with physical data. How can we analyze this data? How can we perform effective cyber physical analysis in order to perform effective threat detection, to analyze threats, right? And then another thing that is of great interest to me is how can we be sure that that the model is correct, that we can trust the model. As I mentioned to you before, a lot of utilities are saying, sure, we like AI, we like ML, everything sounds good. Everybody likes ML now, but how can we trust the output of the model? So topics like explainable AI in cyber physical analysis, it's one of the topics that I'm really interested in. I'm linking into my research at Sandia National Laboratories. And again, as I mentioned, we're hiring, we'd be happy to talk with students, either for internships or maybe that they're interested in the postdoc, to talk with me and just have a discussion around these topics.
I have one more question. Sanjay, you want to come and ask the question?
Yeah. So at the last slide, we can see that the table says the accuracy for the only physical is 100%, then 96 point something, and the 98%. But when we see the plots at this side, we see the for the normal data, we have the that reconstruction error of 5.5 or 6.6. But with the abnormal data, it is 49.46. Also,
is this slide?
Yeah, this slide. So when with the abnormal data, we have such high that reconstruction error, how you are getting like the accuracy. So based on what the accuracy is calculated here, it's only for the normal data, or also the abnormality you are counting for?
No, also for the abnormal. The thing that you see a high reconstruction error on the mid-like graph is showing the reconstruction error of the abnormal data. So the fact that there is so high reconstruction, it helps us achieving a high accuracy, right? Because our threshold is 9. So this means that by putting the threshold to 9, like if we get a threshold of 30 or 40 or 50, this means that it's abnormal for us. So that's why we're achieving like high accuracy. Does it make sense?
Okay. Yeah, that makes sense. Thank you.
What would you do when you don't know how to come up with a threshold, when you have an unseen signature?
So that's the thing. If I thought this is the major problem of production systems, right? So when the machine learning model underperforms, which will happen, not only in cybersecurity use case, like, you know, in all the places that I was working, maybe in a couple of weeks the model was underperforming. When this happens, we have to retrain the model to perform a recurrent training and retrain a model to maybe new unseen data, to new unseen signatures. That's a challenge, and that's something that we have to deal with. Like you know, in my experience, you cannot train a model and just leave it here for a year and just works the same that it was working last year. You know, in my understanding and in my experience, you have to retrain the model very often to achieve that.
Okay, sounds good. Thank you so much for your time this morning. Appreciate George for your this morning, and you will receive a nice plaque from UND and a certificate, and we'll be in touch.
Thank you very much. Thank you, and looking forward to talk to you again.
Yeah, thank you.
Thank you. Bye-bye.